Hello, and a soft welcome to the Galaxy Scientist. It's lovely to share this moment of stillness with you tonight. Wherever you are, allow your mind to drift free of the day's anchor. Let the darkness outside your window feel gentle, like the quiet, velvety space between the stars. We are going to embark on a very slow, very peaceful voyage far from our own world. We will start with the magnificent, familiar sight of Saturn, the ringed jewel of our solar system. But tonight, we're gliding past those icy arcs and venturing into the deep, mysterious territory beyond. We'll explore the hidden moons and the cold, vast expanse where the sun's light is only a memory, seeking out the far frontiers that define the edge of our planetary neighborhood. It's a journey into silence and immense distance, moving like a faint, patient signal through the dark. We'll move slowly, letting the incredible scale of space feel comforting, not overwhelming. If this gentle exploration helps quiet your thoughts or eases you towards sleep, a soft like and a quiet subscribe. Help others find this calm corner of the cosmos, one sleepy mind at a time. When you're ready, let's begin our unhurried drift beyond the rings. The great gas giants linger in the far reaches of our solar family like ancient guardians, immense and patient, shaping the quiet order of the worlds around them. Their gravity spreads outward in invisible tides, stretching across millions of kilometers, reaching even the warm inner planets, with a force that feels almost like a distant whisper. They hold dozens of moons in their arms, guiding each one along winding paths that never quite repeat themselves, as if choreographing a slow, celestial waltz in the dark. These giants do not simply exist at the edge of the sun's light. They steady the entire system, like anchors buried deep in a cosmic sea. Drifting closer to this remote realm feels like floating into deeper water. The sunlight weakens until it resembles a pale silver breath, soft and fragile. Space grows colder, quieter, less touched by the warmth we know. And then, emerging through the dimness like a lantern seen through thick fog, Saturn appears. Its rings shimmer around it in luminous arcs, so thin and delicate that they look as though they could be brushed away by the gentlest touch. Yet they stretch unimaginably far, a vast and graceful halo circling a world of storms. As we draw nearer, the rings reveal their true scale. What seemed like a simple band from afar becomes a layered tapestry of dust and ice, widening into an expanse nearly 280,000 kilometers across in its clearly visible portion. But even that is only the beginning. Beyond the bright stretches lie almost imperceptible sheets of dust and faint wisps of gas, so widely dispersed that they disappear from view unless caught in just the right angle of light. Taken together, the entire structure may extend close to 16 million kilometers from edge to edge, an enormous, luminous veil drifting through space. Despite their incredible size, the rings are nearly weightless by cosmic standards. Their mass is only about 3 times 10 to the power of 19 kilograms, almost 2,000 times lighter than the moon. Most of what composes them is not solid at all. Only around 3% of their volume is actual icy fragments. The rest is made of gas and dust grains so small and so widely spaced that they seem more like a shimmering cloud than anything tangible. To look at them is to realize how something vast can still be fragile, how something mighty can still resemble a dream. These rings are traditionally divided into several wide bands, each with its own character. But when observed through a strong telescope, each wide band dissolves into tens of thousands of thinner circles, each separated by narrow, dark gaps that give the impression of grooves cut into a frozen record. These gaps exist because gravity is always sculpting the rings, tugging, clearing, shifting. Saturn pulls on them. Its moons pull on them. Every orbiting companion carves its own path, leaving behind the faint seams of its influence. Some gaps stretch hundreds of kilometers across, though from a distance they look like the thinnest shadows. The rings reflect sunlight even more brightly than Saturn itself, gleaming like powdered ice. But visibility is a gentle illusion. Some rings remain almost invisible. The inner D-ring, closest to Saturn, is made of crystals of water ice and frozen methane so fine they drift like winter dust. Its upper edge lies roughly 16,500 kilometers above the planet's cloud tops. Its inner edge slowly fades into Saturn's atmosphere, with no clear boundary, just a soft blending of ring into sky. Beyond this sits the brighter C-ring, broader and more substantial. It spans about 17,500 kilometers and contains small fragments up to 2 meters in size. Even so, it accounts for only about 0.033% of the entire structure's mass. The B-ring, further out, shines as the most splendid and massive of all. Beginning around 34,000 kilometers above Saturn's surface, it stretches outward for 25,000 kilometers. Most of it is astonishingly thin, between 5 and 10 meters thick, like a sheet of frost carefully laid across a lake. Yet, at its outermost edge, the material lifts upward, forming a vertical wall 2.5 kilometers high, frozen in place as though raised by a silent tide. The outermost visible ring begins roughly 64,000 kilometers above Saturn's cloud layer and spreads around 14,600 kilometers wide. Here, the ring holds larger pieces, fragments 10 meters or more in size, glistening like drifting shards of broken moons. Embedded among these fragments are small shepherd moons, such as Pan and Daphnis, moving gracefully within the gaps they help maintain. Their presence suggests a history of creation and destruction. Perhaps they are remnants of a larger, icy world torn apart long ago, or perhaps they formed from colliding fragments, slowly gathering themselves into shape. Farther beyond lie the faint F, G, and D rings, almost imperceptible trails of dust and gas. They form a soft envelope around the brighter rings, extending outward in thin curtains that shift with the movements of the moons nearby. Saturn's many satellites influence these rings constantly, stirring them as they pass, sometimes drawing material into their own gravity, sometimes scattering particles back outward like sparks. And then, somewhere in this shimmering realm, a small moon draws attention with an unexpected, gentle pull. Enceladus, a world only about 500 kilometers wide, lies tucked among Saturn's icy companions. It is not large, it is not dominant, and yet it glows with quiet mystery, like a lantern flickering beneath frost. Its surface is covered in ice, bright and smooth in some places, scarred and cracked in others. Beneath this frozen shell lies a secret that sets Enceladus apart from most other worlds. Enceladus is alive with cryovolcanic breath, fountains of vapor and icy grains jetting from fractures in its crust. These eruptions rise like delicate plumes, scattering through the vacuum and sparkling in the faint sunlight. When scientists first studied these emissions, they found unmistakable signs that beneath the moon's surface lies an ocean of liquid water. Models suggest that near the crust's upper layers, temperatures may fall to around 45 degrees Celsius below zero, but at the ocean floor, salts and ammonia dissolved in the water lower its freezing point. allowing the temperature to hover near 0 degrees Celsius. Here, the ocean remains liquid beneath an icy crust, roughly 2 kilometers thick, kept from freezing by the subtle warmth generated through tidal forces. On the surface, the cold deepens. The temperature is near 75 Kelvin, or around 198 degrees Celsius below zero. The atmosphere above this frozen moon is almost non-existent. It consists mostly of water vapor, about 91%, mixed with nitrogen, carbon dioxide, and methane. Each cryovolcanic eruption replenishes the atmosphere for a short while, but Enceladus cannot hold on to it. The moon's gravity is too weak to keep the particles close. They drift upward, escaping into space and flowing outward until they join the delicate haze of Saturn's E-ring. Yet, this loss is balanced by an opposite motion. Enceladus constantly gathers tiny particles, drifting through the region. This ongoing exchange helps maintain the moon's unusual chemical signature. Nothing here is static. Everything circulates, rises, falls, escapes, returns. The timing of the geysers is intertwined with Enceladus's movement around Saturn. As the moon follows its elliptical path, the tidal forces continuously stretch and compress its icy crust. These subtle motions cause fractures to open and close, releasing bursts of vapor and grains of ice. In these plumes, scientists have found complex organic molecules, carbon-based structures more intricate than simple methane or carbon dioxide. They rise from the hidden ocean, carried upward by the moon's breath, hinting softly at the possibilities below. And it is within these hints that the wonder truly lies. Beneath the surface of Enceladus, under layers of untouched ice, warmed by tides and stirred by chemical gradients, there may exist conditions that resemble the environments where life once began on Earth. It is only a suggestion, a distant possibility, but it lingers with a quiet, persistent weight. The organic molecules carried upward by the cryovolcanic jets whisper of potential of chemistry that is not merely cold and barren, but expressive, capable, maybe even promising. These faint clues do not declare anything with certainty, but they suggest that the hidden ocean beneath Enceladus's icy crust, preserved in the quiet dark, warmed from within, enriched by salts and complex molecules, may be a place where the earliest steps of life could take shape. They suggest that, tucked away in a world so small and cold, so far from the sun, conditions in the subsurface ocean may hypothetically be favorable for the genesis of biological life. Beyond the pale breath of Enceladus's distant plumes, another glimmering companion drifts through Saturn's quiet kingdom. It appears first as a faint bead of reflected light, then slowly sharpens into the round, icy form of Tethys, a world that seems to float with patient calm in the frigid dark. From afar, it looks smooth and bright, almost tranquil, yet this serenity masks a history written in cracks, cliffs, and wounds older than memory. Tethys orbits Saturn at a distance of roughly 300,000 kilometers, tracing its path with steady grace. But what makes this moon truly unusual is not only its presence, but its company. Along its orbit travel two much smaller companions, Telesto and Calypso, drifting with it like gentle shadows, each occupying a quiet niche of gravitational balance. These special points, known in the language of celestial mechanics as stable places where forces cancel into stillness, cradle the two small bodies as they move. Telesto lingers 60 degrees ahead of Tethys in its path, like a soft echo leading the way, while Calypso drifts 60 degrees behind, a quiet lantern following the main moon through the deep. Unlike Tethys, Telesto and Calypso are modest in size, measuring only around 20 to 30 kilometers across. They are not grand spheres sculpted by gravity, but irregular shapes, like pebbles caught in slow-motion drift across a frozen river. Their combined mass, only a few trillion tons, feels tiny against the backdrop of Saturn's vast domain, and still, they hold their places with surprising stability, resting in that delicate balance where the pull of the giant planet and the motion of their orbit weave a kind of cosmic hammock for them to drift in. Yet modeling suggests a curious truth. Telesto and Calypso likely did not begin their story here. They do not appear to be children born beside Tethys, molded together in the youth of this system. Instead, they seem like wanderers, travelers who arrived later, captured gently by the balance of forces, settling into their quiet stations ahead and behind the larger moon. Their presence adds a soft note of mystery to the orbit, a reminder that even in the precise mathematics of celestial dance, chance and history find their places. Tethys itself is far larger, measuring about 1,060 kilometers across, made primarily of water ice, with specks of rock hidden within. It is a world so cold that the ice behaves like stone, capable of supporting mountains, ridges, and scars that stretch farther than anything Earth could ever bear. Seen up close, its surface seems bright and ancient, a pale globe marked by the memory of impacts and upheavals long gone silent. Its most striking feature is a gigantic crater called Odysseus, so immense that it spans roughly 450 kilometers, almost half the diameter of Tethys itself. The crater's depth dives down about 3 kilometers, creating a vast bowl of shadowed ice, where faint sunlight slides across ridges like dust on glass. In the soft illumination of Saturn's distant glow, the crater resembles an eye half closed in the cold, watching the empty dark with quiet endurance. Not far from this titanic scar lies something even more astonishing. A great chasm known as Ithaca Chasma, stretching across the surface for nearly 2,000 kilometers. It is a fracture so long it wraps around about 1/3 of the moon's circumference, and so wide up to 100 kilometers that its edges fall away into a bluish, silent abyss. Its depth ranges from 3,000 to 5,000 meters, and its floor is scattered with smaller craters, ridges, and broken ice, like shattered pieces of ancient glass. The origin of this immense wound is still the subject of wondering and modeling. One theory suggests that long ago, Tethys held a subsurface ocean beneath its crust. As that hidden water slowly froze, it expanded, pressing outward with patient force until the outer shell cracked open, splitting like a frozen lake under winter strain. Another explanation ties the chasm to the same colossal event that created the Odysseus crater. The impact that carved such a vast basin could have sent shockwaves rippling through the entire moon, circling around and meeting on the opposite side, creating stresses strong enough to tear open the crust and leave behind a fracture of nearly unimaginable scale. Whether born of freezing oceans or the echo of a violent collision, Ithaca Chasma remains one of the most dramatic features in Saturn's icy realm, a reminder of how even quiet worlds can harbor ancient violence beneath their calm exteriors. Beyond Tethys and its companions, drifting deeper into Saturn's dominion, lies a world unlike any other, a world that glows not with brightness, but with mystery. Titan rises from the distance as a dim, amber orb wrapped in a thick, opaque atmosphere. With a diameter of 5,152 kilometers, Titan is the second largest moon in the entire solar system, surpassed only by Jupiter's Ganymede. It is so massive that it exceeds Mercury in diameter by about 5.5%. Though it carries less mass, yet its size alone is not what sets it apart. Titan is the only moon we know with a dense atmosphere, one that blankets the landscape in a swirling haze so opaque that no ordinary light can reveal the ground below. The air here is cold, roughly 94 Kelvin, around 180 degrees Celsius below zero. Despite this extreme chill and its relatively modest gravitational pull, Titan manages to keep its atmosphere close. This thick layer of air is about 1.5 times denser than Earth's, an enormous cushion of nitrogen, making up over 98% of its volume, mixed with methane and other hydrocarbons. High in this frigid sky, sunlight interacts with the nitrogen and methane. Solar particles stir these gases into more complex organic molecules, weaving chemical threads that slowly drift downward like invisible snow. Over time, these heavier compounds settle onto Titan's icy crust, painting the unseen surface with layers of dark, tar-like material. Because of this smog, a heavy, impermeable veil woven from hydrocarbons, Titan's landscape remains hidden from human eyes in the optical spectrum. Its mountains, plains, lakes, and valleys lie beneath a cloak of amber fog, turning the world into a quiet enigma. Models of Titan's interior add even more depth to its mystery. Beneath the clouded atmosphere lies a thick crust made of water ice mixed with methane hydrate, forming a rigid outer shell several kilometers thick. Beneath this crust rests a cool, salty ocean containing up to 10% dissolved ammonia, a liquid layer that wraps around a dense rocky core, measuring roughly 3,400 kilometers in diameter. The pressures and temperatures here twist ice into unfamiliar forms, making it behave not like frozen water on Earth, but like a hard mineral. These ice layers build mountains, ridges, and solid plateaus, sculpting a surface that is at once alien and strangely familiar. In the lowlands and deep chasms, Titan holds lakes not of water, but of liquid ethane and other hydrocarbons. These dark, glassy bodies pool in basins carved over eons, reflecting the dim light that filters through the smog above. They are the only stable surface liquids known beyond Earth, cold and ancient, lying beneath a sky thick with chemical haze. Titan's atmosphere is constantly under siege from the solar wind. Particles streaming from the sun, guided and amplified by Saturn's powerful magnetic field, strip away gases from Titan's upper layers. And yet the moon persists. Internal processes, likely involving cryovolcanic release and the chemical breakdown of methane within the lower atmosphere, continually replenish what is lost, maintaining Titan's dense air over spans of time so vast that the moon will not lose its atmosphere for billions upon billions of years. But time moves differently when measured in cosmic scales. One day, far in the future, long after humanity has passed its brief age, the sun will swell into a red giant, pushing its warmth far beyond its current reach. When that distant era arrives, Titan's dense smog may be burned away, the frozen surface may thaw, and the hydrocarbon lakes may evaporate, transforming landscapes beyond anything we can imagine. In such a future, Titan may become warm enough, bright enough, and open enough to host conditions far more favorable to the genesis of life. But that moment lies in an age so distant that it lives only in the quiet speculation of astronomers, tucked into eras the universe itself must patiently await. And yet, for now, Titan remains a world locked in cold secrecy, an amber sphere orbiting in the dim light of its giant companion, holding oceans and landscapes we cannot yet see, breathing with cycles of methane rain and organic mist. Of course, Saturn's realm stretches far beyond the icy stillness we have just drifted through. And as the quiet glow of that distant system deepens around us, Titan begins to reveal itself once more. No longer only the mysterious lantern glimpsed through amber haze in the previous part of our journey, but now a world opening slowly beneath our gaze. A world where cold and chemistry braid together into landscapes unlike anything else we know. Titan circles the sun from a distance of roughly 10 astronomical units, far beyond the warm cradle of the habitable zone. At such remoteness, sunlight arrives only as a dimly faded memory, a thin wash of gold that barely warms the sprawling air of this moon. And yet, despite that faintness, Titan endures in quiet grandeur, the largest of Saturn's many companions. It drifts far outside the Great Rings, orbiting roughly 1,200,000 kilometers from the planet's center, holding its place along a nearly circular route. One full journey around the gas giant takes a little less than 16 Earth days. Though here, time feels slower, heavy, almost syrupy, and 16 days seem to stretch and widen into something far more ancient. Its diameter is about 5,152 kilometers, a little more than 5.6% larger than Mercury, though its mass is far smaller, only about 1.35 times 10 to the power of 23 kilograms, roughly 40% of Mercury's heft. These numbers, faint as they are when whispered into the night, remind us that Titan is built differently from the rocky worlds we know. Its average density is only about 1/3 that of Earth, suggesting a body formed from ice, stone, and exotic compounds, shaped in the cold hinterlands of the solar system. Peering deeper into the moon's imagined cross-section, we find a heavy core, roughly 3,400 kilometers in diameter, made of silicon-rich rock and ancient minerals compressed through uncountable ages. Around it lies a dense layer of ice, hard, closely packed, and plunged into darkness where the pressure turns it into something closer to stone than the fragile frost known on Earth. This ice forms the floor of a massive subsurface ocean, a cold and hidden sea stretching hundreds of kilometers deep. Its waters are not pure. They are laced with ammonia, methane, and caustic salts that lower the freezing point far below what we would consider possible, allowing this ocean to remain liquid, even in temperatures that fall well below what we would call deadly cold. This ocean, wrapped in shadow and silence, is sealed in by a crust about 100 kilometers thick, made of water ice and methane hydrate, interwoven like the fibers of a frozen tapestry. Above, Saturn's tidal pull slowly kneads the crust, flexing it so gently that the motion would be imperceptible to touch. But over time, these forces open fractures and faults through which the deep ocean sometimes exhales. Through these wounds, cryovolcanoes burst forth, releasing plumes of methane, ammonia, and water that settle back onto the surface, or drift as haze into the immense sky. Methane here plays a role much like water vapor on Earth. Titan's average surface temperature, around 94 Kelvin, roughly 179 degrees Celsius below zero, pushes methane to the edge of boiling. The slightest fluctuation in surface temperature can cause methane vapor to condense, forming liquid droplets that fall as rain. Over time, these rains carve river channels, feed lakes, and gather in seas smooth, dark expanses of hydrocarbons pooled in the moon's lower terrains. In the dim light that filters through the haze, these seas shine not with blue reflections, but with muted, metallic gleams. Titan's atmosphere is dominated by nitrogen, comprising nearly 98.4% of its volume. Methane, makes up about 1.6%. The cold grips the lower air so tightly that it clings close to the ground in a condensed layer, quieting the world and muting its horizons. Mountains rarely rise more than 500 meters from this smothering blanket. Their outlines soften in the eternal twilight. Most of Titan's surface remains hidden from human sight, concealed beneath a swirling orange-yellow haze formed by droplets of liquid methane mixed with complex organic molecules. These tiny particles hover in suspended fogs that absorb and scatter visible light, letting only infrared warmth seep through. This effect, opposite to the greenhouse phenomenon familiar on Earth, cools Titan's surface even further, dropping temperatures by an additional 10 degrees. Though this haze obscures the surface, the Cassini orbiter used infrared vision to pierce the smog, revealing the world below patchy, textured, contrasting in ways that feel both alien and strangely peaceful. Titan's face is mottled with bright and dark patches, some reflecting nearly all the light that reaches them, others absorbing it into their ancient soils. Slightly south of the equator lies a luminous region named Aztlan, where the land gleams faintly through the haze. In this area stands Mount Doom, or Doom Mons, a mountain rising about 1.5 kilometers above the plains around it. Its base sprawls for 60 kilometers, its summit ringed with craters, and its slopes etched with signs of turbulent flows. These traces, still sharp against the icy terraces, whisper that this could be an active cryovolcano, its inner workings slowly shaping the moon's surface. To the northeast lies Sotra Patera, Titan's deepest known depression, a basin nearly 30 kilometers long, dropping around 2 kilometers below the surrounding plains. Its jagged curves and steep walls resemble the mouth of a great wound. Many believe this chasm marks the opening of another cryovolcano, part of a larger tectonic structure that includes Doom Mons itself. These regions form a connected system of vents and fractures through which Titan's hidden ocean may have once or may still breathe. North of Doom Mons spreads Mahini Fluctus, an immense area blanketed by the outflows of cryovolcanic eruptions from Doom Mons. The region extends roughly 180 kilometers, shifting from a width of 15 kilometers in its southern reaches to about 60 kilometers in the north. Here, frozen materials once poured over the land like icy lava, mingling now with broad dunes of sand-like grains composed of frozen methane and fine water ice. Seen from above, these dunes ripple in gentle patterns, shaped by Titan's winds, soft, slow, and cold. Continuing gently westward, the landscape darkens into an area known as Fensel. Within it, the largest impact crater on Titan can be found, Minerva. It stretches across 440 kilometers, dwarfing any other crater on the Moon by nearly threefold. Its floor sinks only about 200 meters, and the mountains ringing it reach heights of less than 500 meters, soft contours worn down by time. Minerva is believed to be one of Titan's oldest scars, with estimates placing its age between 300 million and 1.2 billion years. Erosion and tectonic motions have softened its features, blurring its edges, but the crater's sheer size keeps it visible from orbit. Minerva's inner structure is still distinct. At its center lies a flat plain, encircled by a ring of low hills. This region, about 200 kilometers wide, reflects light more readily than its surroundings, making it noticeable even through Titan's thick haze. Around it lie darker plains, so-called moats, that extend for about 50 kilometers. These give way to outer ridges that mark the crater's perimeter, forming a ghostly boundary in the dim light. Moving slowly toward the south, the horizon brightens again, revealing one of Titan's most unusual landmarks. Haute Arcus. This luminous, arc-shaped region spans roughly 600 kilometers, standing out sharply against the muted hues around it. Radar readings from Cassini show that Haute Arcus sits at the border between rugged, rocky highlands to the northeast and a vast valley stretching northwest. Some portions of this arc seem to change tone over time, possibly due to fresh cryovolcanic deposits settling upon the surface or evaporating into the air. From high above, faint channels resembling riverbeds meander outward from the mountains of the Haute region toward the northwest. There lies Xanadu, a sprawling lowland marked by rugged, fractured terrain. Its northwestern edge rises into the Mithrim Montes, a trio of parallel ridges stretching around 150 kilometers, their average height close to 1.9 kilometers. Among the summits of the southern range stands Titan's highest peak, 3,337 meters tall, an icy giant overlooking the ancient plains. From its crest, looking westward, one might imagine a vast, dark expanse stretching for several hundred kilometers. This region is called Shangri-La, thought to have once held liquid methane pooled in broad basins or tucked beneath a layer of topsoil, like underground aquifers on Earth. Though relatively flat and lying below average elevation, Shangri-La hosts lighter patches of raised terrain, perhaps remnants of islands that once jutted above a hydrocarbon sea. West of Shangri-La gleams Adiri Uplands, a bright region spreading for nearly 2,500 kilometers. Its valleys and slopes are carved by countless drainage channels and punctured by caverns, all clearly visible in infrared imagery. Scientists believe these features formed under torrents of liquid hydrocarbons that once coursed through the region, leaving behind tunnels, grooves, and branching patterns reminiscent of river systems on Earth. To the west of Adiri lies the broad, dark lowland known as Balat, and just to the east, near the border where Shangri-La's ancient plains meet brighter ground, stands a place of quiet significance, the Huygens landing site, where a small human-made visitor once rested upon Titan's frozen soil, listening to the soft whisper of the moon's distant winds. So far, only a single human-made craft has ever touched the surface of a world in the distant outer solar system, and the quiet significance of that moment still echoes gently through our understanding of Titan. Long before its small metal feet pressed into that frozen ground, the journey had already begun, quietly, patiently, when two companions left Earth together. The Cassini orbiter and the little descent probe it carried deep within its structure like a heartbeat, the Huygens lander. They slipped away from our world in 1997, leaving behind the blue glow and heading into the long night that stretches beyond Mars and Jupiter, into the cold realm where sunlight thins to a pale ribbon. For 7 long years, the pair drifted between the planets, passing through regions where darkness pools like deep water. Then, early in 2004, Cassini entered Saturn's orbit, settling into a slow, looping path among the planet's moons and rings. The great journey was not over. In many ways, it had only reached its midpoint. In the opening days of 2005, Huygens separated from Cassini and began drifting toward Titan, alone now, like a tiny seed falling through a twilight sky. Cassini remained high above, circling the giant planet in wide, elegant arcs, continuing its scientific work while serving as a relay station, a listening ear in the distant dark, ready to collect the faint signals Huygens would send back during its descent. And descent it was, long and gentle. For just under 2.5 hours, Huygens sank through Titan's layered atmosphere, falling through sheets of haze, as if descending through folds of soft, dim fabric. Parachutes opened in careful sequence, one after another, slowing the lander's drop until its speed softened to only about 4.4 meters per second. At one moment, the craft endured 15 times Earth's gravity, a sharp press of force. But the little lander held steady, trembling but unbroken, protected by still air and its own resilience. When Huygens finally touched down, the surface beneath it came into focus, a muted landscape drawn in tones of amber and dim gold. Rounded stones lay scattered across a flat plain, their smooth shapes suggesting that long ago, some form of flowing liquid, perhaps methane, perhaps something stranger, had shaped them. Beneath the pebbles lay a soft yet dense material, something like wet sand or heavily packed snow. A drill extended gently downward, sinking 15 centimeters into the surface. As it disturbed the soil, methane gas escaped into the air in faint puffs, as though Titan exhaled a quiet greeting to the visitor resting upon it. During its brief life on Titan, Huygens sent back around 500 megabytes of precious scientific data, including about 350 images windows into a world no one had ever seen up close before. The moon's atmosphere revealed itself in layers, dense, obscuring, yet filled with delicate mysteries. One discovery came as a surprise even to seasoned scientists. At an altitude of roughly 80 kilometers, Huygens detected a remarkably still zone, a layer of atmosphere where neither upper winds nor lower breezes could intrude. It existed like a silent, floating border, an invisible boundary dividing Titan's atmosphere into two distinct realms. But Titan held yet another secret, not one, but two ionospheres. The upper layer, at around 1,200 kilometers, teemed with charged particles sculpted by cosmic rays and the faint touch of solar wind. The lower ionosphere, floating near 60 kilometers, seemed to arise for reasons still not fully understood. Together they formed two invisible shells, stacked like quiet halos, glowing faintly in ways only instruments could see. When we drift northwestward from the bright Adiri terrain, Titan's largest sea unfolds, Kraken Mare, a cold, dark expanse of liquid hydrocarbons covering over 400,000 square kilometers. It lies still and heavy, its surface smooth enough to resemble polished stone. The sea is so thick with methane and ethane that its depth remains a mystery. Only one thing is certain: most of it extends far beyond 200 meters. Beneath the dim amber sky, Kraken Mare reflects light like a restless mirror. A little farther north sits Ligeia Mare, nearly 500 kilometers across, its surface spanning roughly 100,000 square kilometers, 3 times the size of Earth's Lake Baikal. This sea, too, is quiet and shadowed, connected to Kraken Mare by the narrow Trevis Fretum Channel, around 173 kilometers long, where liquid methane flows in slow, unseen currents. Near Titan's southern pole lie many smaller lakes and lagoons, scattered like drops of chilled ink upon the land. In 2014, when scientists examined older Cassini images of Ligeia Mare, they noticed something astonishing. A bright patch had appeared on the sea's surface, a feature not present in earlier photographs. Over a span of months, it grew until it reached a diameter of roughly 260 kilometers, then vanished almost instantly, without leaving a mark. One hypothesis suggests that shifting temperatures stir the deep layers of the sea, releasing nitrogen bubbles that cluster at the surface into persistent rafts of bright foam. Because Titan's hydrocarbons are thick and syrup-like, these bubbles can grow to as much as 4.5 centimeters across and endure for months. Seen from orbit, such floating clusters reflect infrared light strongly, appearing as luminous islands that come and go with the changing seasons. Had a Titan submarine been built and sent during the early 2010s, as once imagined, such foam islands would have posed a considerable challenge, masking the surface, confusing instruments, hiding currents beneath dense patches of shimmering bubbles. But that mission was eventually set aside. Another idea took priority, one that felt more agile, more adaptive, more in harmony with Titan's gentle winds. Dragonfly. This future rotorcraft, still under development, will visit Titan not as a rover, not as a lander, but as a flying explorer, a noctocopter with 4 twin sets of blades. Dragonfly will be able to remain aloft even if several blades fail. Its design has just passed key tests, and launch is scheduled for 2027. Dragonfly will carry a radioisotope thermoelectric generator strong enough to lift it to altitudes of nearly 4 kilometers and to glide across Titan's plains at speeds of about 36 kilometers per hour. It will touch down, sample the soil, then rise again, carrying the landscape into its memory as it flies from place to place. Its instruments are as varied as they are sensitive. Cameras will capture wide panoramas as well as close, detailed studies of rocks and dunes. A mass spectrometer will analyze atmospheric gases and the inner structure of surface materials. Through these tools, Dragonfly may whisper answers to questions we have carried for decades. Do we have even the faintest chance of encountering primitive life on Titan? On one hand, Titan's surface seems too cold, too hostile. The temperature hovers around 94 Kelvin, about 179 degrees Celsius below zero. Hydrocyanic acid, a deadly compound, lingers in the air. Liquid water is absent on the surface. By the standards of Earth biology, Titan is a place where life should not exist. And yet, the Moon's atmosphere is a treasure chest of organic molecules. Nitrogen-bearing compounds drift downward like soft rain. Amino acids, fundamental building blocks of proteins, may be synthesized naturally in the haze. Methane, in its liquid form, could serve as a solvent, playing a role analogous to water in chemical reactions. Laboratory experiments show that mixtures of liquid hydrocarbons and phosphane can form something akin to the primordial soup that once cradled life on early Earth. If life were to exist on Titan, it would be unlike anything we know, slow-moving, cold, shaped by methane instead of water, formed in an environment where energy trickles rather than flows. But life in any form needs certain ingredients: liquid, energy, and chemical diversity. Aside from Earth, several places in the solar system might satisfy these conditions. Mars remains the most studied and perhaps the most promising. Mars is not the only possibility. Beyond its orbit, farther from the familiar warmth of sunlight, there are worlds that keep their secrets tucked beneath ice and drifting haze. Places that wait with a quiet patience, holding their chemistry like a lantern cupped in both hands. Sometimes, all it takes is a small shift in perspective, a gentle turning of our gaze to find another path, another destination, and so the next world draws near, not closer to the sun, but away from it, pulling us toward the vastness where Jupiter hangs like a colossal beacon in the dark. Jupiter, the giant among giants, is the largest planet in our solar system, a world so massive that it outweighs Earth by a factor of 318. Approaching it feels like drifting toward a storm frozen in time, a whirl of colors and winds arranged across a sphere made almost entirely of hydrogen and helium. Mixed within its atmosphere are faint traces of methane, ammonia, sulfur, nitrogen-based compounds, and ice crystals that flash like distant sparks. For all its beauty, Jupiter is a place where life, as far as we can imagine it, could hardly endure. There is no solid ground to stand on, no place where a living creature might find shelter. The planet's deep layers crush inward, under pressures that defy imagination. Temperatures soar to extremes, and the gases themselves coil in an endless dance that leaves no room for fragile biology. But Jupiter is not alone. It carries with it a family of moons, dozens upon dozens of companions, but 4 of them shine more brightly in the story of exploration: Io, Europa, Ganymede, and Callisto. Galileo Galilei first observed these 4 in 1609, when the telescope was still new to human eyes. Seen from afar, they appear faintly comparable to Earth's moon or Mercury in size, but up close, they are worlds of astonishing individuality. Weathered ice, ancient craters, hidden seas, and restless geology give each moon its own presence, its own voice in the silence of space. It is believed that Jupiter still radiates more heat than it receives from the Sun, having retained energy from the moment it was born through gravitational contraction. Because of this, the planet glows faintly from within, like a coal that never fully cooled. With all its moons tracing their orbits around it, Jupiter becomes a kind of miniature solar system, a model in which light and gravity and motion form a smaller echo of the grand design. At first glance, Jupiter's moons might seem unpromising in the search for life. They lie far from the Sun, swathed in ice, with atmospheres too thin to protect anything warm or breathing. And yet, when looked at closely, they reveal something extraordinary. Beneath their frozen crusts, 3 of the 4, Callisto, Europa, and Ganymede, are believed to hide vast oceans of liquid water. The estimate is not casual. It is supported by careful measurements that suggest these oceans may exist in layers beneath the ice, sheltered from the harsh vacuum of space. These subsurface seas could offer stable environments, warmed not by sunlight, but by tidal forces and internal heat. A thick shell of ice can protect the waters below from radiation, from meteoroid impacts, and from the emptiness of the cosmos. The ice becomes both shield and insulation, holding warmth where it might otherwise be lost. In such places, life, if it ever arises, may do so not under a bright sun, but under kilometers of protective crystal, in darkness lit only by chemistry and heat. Among Jupiter's moons, one stands out in size and complexity: Ganymede. It is the largest of all the satellites. Not only Jupiter possesses, but in the entire solar system, surpassing even Mercury in diameter. With a radius of 2,634 kilometers, about 8% larger than Mercury, Ganymede feels almost like a planet in its own right, a world caught in eternal orbit around a greater world. Its mass is equally impressive, about 1.48 times 10 to the power of 23 kilograms, roughly twice the mass of Earth's moon. Yet size is only the beginning of its strangeness. Ganymede is the only moon known to have a liquid metal core, a churning heart that generates its own magnetosphere, a magnetic bubble that envelops the moon like a faint, invisible shield. Deep inside, nuclear decay contributes to the warmth that keeps this internal engine running. And though the surface temperature remains frigid, around 110 Kelvin, which is about 163 degrees Celsius below zero, the interior may be far hotter. Estimates suggest the core could reach temperatures up to about 1,700 Kelvin, a glow hidden under thick layers of ice and rock. Evidence gathered by the Galileo spacecraft suggests the presence of a vast, salty ocean below Ganymede's frozen shell. This ocean may lie as deep as 200 kilometers or more beneath the crust. Even more intriguing, it is believed that this ocean does not exist as a single uniform layer, but as several stacked oceans, perhaps as many as 4 distinct layers. Each one holds water of different salinity, density, and temperature, separated by thin layers of ice, acting like boundaries between worlds. One might imagine them as floors of a silent subterranean cathedral, each one colder or warmer, more or less salty, shaped by pressures we can hardly fathom. On the surface, spectrographic observations reveal something subtle but fascinating. Ganymede possesses a rarefied oxygen atmosphere. It is exceedingly thin, nothing like Earth's air, and far too delicate to support life on its own. Its presence does not prove biology. Rather, it likely forms when ultraviolet radiation strikes surface ice, splitting water molecules into hydrogen and oxygen. The hydrogen, being lighter, escapes into space, leaving the heavier oxygen behind, which gathers low over the icy plains. It is a whisper of a process, slow and ancient, unfolding over millions of years. Alongside the oxygen, other substances have been detected on Ganymede's surface: carbon dioxide, sulfur dioxide, various sulfates, and several kinds of organic materials. They might have been brought up from the subsurface ocean or formed through chemical interactions in the upper layers of the crust. But the pathways that delivered them or shaped them remain uncertain. These compounds sit upon the ice like fragments of a story not yet fully translated, hints of chemical possibilities that stir the imagination but refuse to reveal everything. Ganymede's exterior is dotted with patterns, bright grooved terrain, dark ancient regions, intersecting ridges that hint at tectonic motion frozen in time. In some places, the ice seems to have fractured and shifted, leaving scars that stretch across continents. In others, the surface is softly cratered, as though shaped by gentle blows rather than violent impacts. Its magnetosphere interacts with Jupiter's immense magnetic field, twisting and flexing in a dance of charged particles no human eye could ever witness directly. The moon's auroras sway near its poles, faint but real, shimmering in ways only instruments can detect. When imagining these distant landscapes, one might picture walking across Ganymede's icy plains, not in reality, of course, but as a quiet dream. The ground would creak faintly beneath your boots, and the horizon would glow with Jupiter's reflected light, casting long shadows that shift with the moon's slow rotation. Beneath your feet, oceans lie hidden, their waves locked beneath hundreds of kilometers of ice, and deep within, the liquid core spins and murmurs, unseen yet constant, keeping Ganymede's magnetosphere alive. All these details reveal a moon not simple or silent, but complex and layered, a world shaped by forces both gentle and immense. Water, salts, metals, radiation, and time weave together in ways we have barely begun to understand. The thin oxygen atmosphere, the multitude of icy layers, and the possibility of stacked oceans speak of geological processes that may have been active for billions of years. The carbon dioxide, sulfur compounds, and organic traces invite questions about chemistry that has unfolded slowly and without interruption, quietly painting the surface with hints of what might lie below. Though nothing discovered so far proves the presence of life, Ganymede remains a world where the foundations of habitability persist, sheltered, protected, and evolving out of sight. The layers of ocean beneath the shell could harbor conditions warm enough and stable enough for some form of biology to one day emerge, or to have once flickered into being. For now, these ideas remain possibilities, offered like fragments of a mystery, waiting in the dark. The moon's surface materials, with their mixture of frozen water, carbon dioxide, sulfur dioxide, sulfates, and organic compounds, may trace their origins to the depths of those hidden oceans. But the pathways by which they rise or settle, the processes that shape them and leave them scattered across the frozen crust, are still not clear. Callisto lingers at the edge of Jupiter's great family, like a distant lantern, dim, steady, and quietly enduring. It does not shine with Europa's restless fractures or Ganymede's magnetic mysteries. Instead, it seems to remain in a kind of ancient stillness, as though time has folded around it and left its surface almost untouched for billions of years. Yet when we drift closer, letting the soft light from Jupiter spill over its frozen plains, something deeper begins to emerge. Callisto is not silent at all. It simply speaks in a slower, older language. This moon is the second largest among Jupiter's companions, and the farthest of the 4 great Galilean satellites. With a diameter of 4,820 kilometers, remarkably close to the size of Mercury, it feels less like a moon and more like a world that simply chose a quieter path. From far away, it looks dark and mottled, as if dusk has settled permanently across its surface. But when the light glances off the ice, delicate hints of color flicker like frost catching the first touch of morning. Callisto's crust is thick, somewhere between 80 and 150 kilometers of solid ice. This outer shell shields a world beneath, a salty ocean infused with ammonia and other impurities, substances that lower the freezing point of water and allow a liquid layer to survive even under temperatures around 251 Kelvin, roughly 21 degrees Celsius below zero. The ocean itself may be anywhere between 50 and 300 kilometers deep. Imagine that, an entire ocean, perhaps larger than any on Earth, locked beneath a vault of frozen time, stirred only by chemistry and pressure. Below that ocean, deeper still, lies another layer of ice, perhaps 300 kilometers thick, and beneath that rests Callisto's core, a blend of rock and frozen water, pressed together by slow cosmic ages. The layering resembles a cross-section of a dream, ice above water, in the middle, ice again, then rock, each level stacked upon the next, like pages of a story written in darkness. The surface of Callisto, however, is one of the most heavily cratered in the solar system. It has absorbed the history of the cosmos on its skin, preserving every impact with reverence. The craters lie so densely upon one another that in certain regions, the moon looks like a mosaic of ancient scars. Yet, the quiet is comforting, almost meditative. Nothing seems rushed here. Nothing seems violent now, even though the surface was shaped by violence long ago. When light from the sun, or from Jupiter's reflected glow, bounces off Callisto, spectrometers pick up an array of chemical signatures: water vapor, silicate rocks, ammonia, carbon dioxide, sulfur compounds, iron, magnesium, and tholins. Tholins, complex organic polymers containing nitrogen, emerge when ultraviolet light alters simple molecules on icy surfaces. They settle like powders of rust, wine, and violet. These subtle tones give Callisto an oddly warm appearance, despite the brutal cold. They are reminders that chemistry continues quietly even in the far outer reaches of the solar system. Yet for all these intriguing materials, Callisto's prospects for life remain dim. It lies too far from Jupiter to gain meaningful warmth from tidal heating. The giant planet's gravitational pull is too weak at this distance to need Callisto's interior. meaning the friction that warms Europa and Ganymede never takes place here. Without that heat, the ocean remains cold and largely still. And because much of Callisto's interior is ice rather than rock, fewer mineral-rich interactions occur, interactions believed to be deeply important for biological beginnings. The temperature is low, the chemistry is modest, and the environment quiets itself into states where life, as we imagine it, would find little nourishment. Even so, the possibility cannot be fully dismissed. Callisto's ocean could hide structures and energies that we do not yet understand, and in the vast cosmic sea, even quiet worlds may keep their own surprises tucked away beneath layers of frost. Yet, among all of Jupiter's moons, the one that draws the most hopeful whisper of life is Europa. Despite being the smallest of the 4 Galilean moons, Europa feels immeasurably alive, not in the sense of forests, creatures, or warmth, but in the restless shifting of its surface, its tidal stresses, its hidden ocean that seems always on the edge of revealing itself. Europa is slightly smaller than Earth's moon. Its surface temperatures are bitterly cold, around 110 Kelvin at the equator, which is roughly 163 degrees Celsius below zero, dropping even further to about 50 Kelvin, or 223 degrees Celsius below zero, near the poles. It is tidally locked to Jupiter, showing the giant planet the same face at all times, yet its actual behavior is more complicated. Subtle wobbles in its rotation suggest that its outer shell moves separately from its deeper layers, as though the entire crust glides over something fluid. This suspicion was confirmed by the Galileo probe. Measurements of Europa's interaction with Jupiter's magnetic field revealed a conductive layer beneath the surface, most likely a briny, global ocean. Europa's surface carries long, sweeping fractures that trace the moon's skin like a web of ancient roads. Some of these cracks indicate that the crust has rotated up to 80 degrees relative to the interior. Such motion would be impossible if the crust were frozen solid all the way through. Something must be allowing the outer shell to drift something liquid, something deep. Jupiter's immense gravity exerts tidal forces on Europa, flexing and stretching the moon with each orbit. This constant kneading generates frictional heat, enough to maintain an ocean of liquid water beneath the ice. Estimates suggest this buried ocean may reach depths of up to 100 kilometers. Even more astonishing, its total volume may be twice that of Earth's global ocean. Imagine the weight of that much water pressing inward, whispering against the underside of the ice, moving in slow, dark currents untouched by sunlight for billions of years. Europa's surface is unusually smooth, one of the smoothest in the solar system. Most of its features rise only a few hundred meters above or below the average level, giving the moon a polished, almost ethereal appearance. The ice crust may be between 10 and 30 kilometers thick, though some of the deeper fissures may descend far enough to graze the ocean beneath. To scientists, these cracks are not scars, but windows. They give access, however briefly, to samples of material that might hold clues to the moon's concealed geography. Europa also displays one of the most spectacular natural phenomena in the outer solar system: ice-cold vapor geysers. These plumes erupt when Europa reaches the farthest point from Jupiter during its orbit, a time when the tidal stresses shift just enough to stretch the crust more dramatically. When active, the plumes can reach heights of up to 200 kilometers, soaring into space as pillars of near-pure water vapor. The vapor is astonishingly clean, carrying only hints of other compounds. This purity makes the plumes tantalizing for scientists. They could be pathways from the ocean below, or they might originate from massive reservoirs trapped within the ice itself. Each possibility paints a different picture of Europa's internal geography, yet both deepen the Moon's allure. To uncover more about Europa's ocean, researchers study the central basins of the Moon's largest impact craters. Only a sufficiently massive object can break through the multi-layered ice and expose the liquid beneath. When such an impact occurs, water wells upward, then freezes, preserving minerals from the subsurface ocean. Spectral analysis of these frozen remnants shows a complex blend of magnesium, sulfur, and various sulfur-oxygen compounds, along with hydrogen peroxide and strong acids. Such chemistry suggests that Europa's ocean is not merely water, but a dynamic mixture of minerals, salts, and oxidants, a potentially fertile environment for life's earliest reactions. Europa's atmosphere, though extraordinarily thin, about 1 trillion times thinner than Earth's, is rich with oxygen produced through ultraviolet radiation interacting with surface ice. Hydrogen escapes into space, leaving the heavier oxygen behind. Over aeons, some of that oxygen may migrate downward into the subsurface ocean. If true, Europa's ocean could contain enough dissolved oxygen to support simple aerobic organisms. Imagine, deep within the darkness, hydrothermal vents on the ocean floor. They may release heat and chemicals into the water, creating pockets of warmth and nourishment, much like the vents on Earth's deep seabeds, where life thrives without sunlight. Primitive organisms might cling to the underside of the ice crust, feeding on chemical gradients. Others might float freely, drifting between mineral-rich upwellings like tiny lanterns carried by unseen tides. Some early ideas even suggested that simple multicellular creatures might inhabit Europa's ocean. While these claims may have been optimistic, they were not entirely implausible. On Earth, many species, bacteria and multicellular organisms alike, survive in conditions similar to those expected beneath Europa's ice. Tardigrades, for instance, endure extreme cold, intense pressure, radiation, and long periods without water. They demonstrate that life is capable of thriving in places that once seemed impossible. And so, even with Europa's frigid temperatures, even with its kilometers-thick shell of ice, even with oceans hidden in darkness for billions of years, we cannot rule out the possibility of primitive life, originating in the depths of this celestial object of its own accord. Even if Europa's hidden ocean stirs with the possibility of something living, our understanding of it is still more dream than detail. We stand very far away, listening only through instruments and echoes, and for all the care with which we imagine its darkness and its buried waves, there is a simple truth that threads through everything we have spoken of so far. We have barely touched these worlds at all. Despite how deeply we wonder about Jupiter and its moons, our visits to them have been brief and distant, like passing a house at night and catching only a glimpse of light in one window. No spacecraft has ever landed on any of the giant planet's satellites, and certainly not on Jupiter itself, whose swirling gases cannot offer a surface to stand upon. We have only flown by, orbited, measured from afar, letting cameras and fields and particles tell us their quiet stories while we drift on. For now, the largest planet in our system is being watched over by a lone emissary, the Juno spacecraft. It loops around Jupiter in a long, stretched-out orbit, diving close to the cloud tops, then soaring outward again, each pass tracing a new arc of data through the darkness. Its purpose is to study the gas giant itself in patient detail, its gravity, its deep winds, its magnetic heart. But after a time, its attention will widen. Plans called for Juno, as early as the middle of the decade, to slowly adjust its path and begin passing closer to the Galilean moons, brushing by them like a quiet visitor listening to the signatures of their ice and stone from only a little way above their frozen skins. The information gathered by Juno is more than a collection of measurements. It is a way of untangling the processes that shape Jupiter's entire system, from the depth of its atmosphere to the edges of its magnetic field. Each orbit refines our picture, bringing into focus how the planet's immense gravity, radiation, and internal heat influence everything that circles it. Piece by piece, a clearer portrait emerges not only of Jupiter as a world, but of the environment that Europa, Ganymede, Callisto, and their smaller companions must endure. Our curiosity, of course, does not end with a single spacecraft. In the early years of the 21st century, the European Space Agency began work on a mission with a name that sounds almost like a promise: the Jupiter Icy Moons Explorer, often shortened to JUICE. Its purpose is as gentle as it is ambitious: to travel all the way to Jupiter and dwell among its icy moons, studying the gas giant itself, along with Ganymede, Europa, and Callisto in far more detail than any previous visitor. Once launched from Earth, JUICE will spend years crossing the inner system before finally reaching Jupiter's neighborhood near the end of the next decade. Its mission is expected to stretch on for several years afterward. Over that time, it will circle, approach, retreat, and circle again, tracing careful paths that bring it near the moons whose oceans and crusts hold so many of our questions. If all goes as planned, our understanding of the giant planet and its satellites will grow not in sudden revelations, but in a slow accumulation of gentle certainties, new maps of surfaces, new readings of interiors, new glimpses into how ice, rock, and water behave under alien conditions. Alongside JUICE, another great project is taking shape across the ocean: NASA's Europa Clipper, where JUICE will share its attention among several targets. Europa Clipper is being designed with a more focused devotion. Its heart is set on Europa. The plan is for the spacecraft to leave Earth sometime in the early 2020s and arrive in Jupiter's domain in the early 2030s. Rather than orbiting Europa itself, it will enter into orbit around Jupiter and then perform dozens of close flybys of the icy moon, sweeping low again and again over different regions. Each pass will let it taste a little more of Europa's subtle environment: the thickness of its ice, the chemistry of its plumes, the shape of its gravity field, the texture of its fractured surface. It will listen to the moon's whispers in magnetic lines and particles, looking for signs that confirm what we now only suspect: that below Europa's frozen crust, a global ocean exists with the right ingredients, the right energy, and perhaps the right history to cradle something living. Together, missions like JUICE and Europa Clipper are not simply technical projects. They are gentle acts of reaching out, of extending our senses toward worlds that might, in their own distant way, be capable of holding life. Yet even as we focus on Jovian moons and their buried seas, our quiet journey through the solar system invites us outward once more, into a different kind of frontier. Between the orbits of Mars and Jupiter lies a broad, faintly haunted region, the main asteroid belt. At first glance, it might seem like little more than a ring of debris, a cluttered band of rocks left over from long ago. But, as with so many things in the cosmos, looking more closely reveals a richer and more intricate story. Today, more than 300,000 small bodies in this region have been catalogued with numbers and names, and the true count may exceed 1 million. The belt's modern story began in 1801, when astronomers searching diligently for a missing fifth planet noticed a strange object in the sky. Its brightness and apparent position suggested a world, Yet it appeared in telescopes not as a disk, but as a point of light, no larger than a star. This first discovery was named Ceres. Soon, other objects of similar kind were found, each too small to show a visible disk. To describe them, astronomers chose a new word: asteroids, literally, star-like ones. The asteroid belt is not made only of rocks. It is suffused with fine cosmic dust, the leftovers of collisions and slow grinding over unimaginable spans of time. As this dust spirals in toward the sun under the subtle drag of light itself, its tiny grains scatter sunlight in a soft, diffuse glow. From dark places on Earth near the equator, this glow can sometimes be seen by the naked eye as a pale, triangular column rising along the path of the zodiac. It is called the zodiacal light, a ghost of the solar system's own debris, shining faintly in the night. For a long while, people imagined that the asteroid belt was the shattered corpse of a single world, a planet that had somehow been destroyed. But as measurements improved, that hypothesis began to falter. First, the total mass of all objects in the main belt turned out to be far too small. Add them all together and you get only about 3 times 10 to the power of 21 kilograms, roughly 4% of the mass of Earth's moon. Even if we allow that many objects could have been lost or scattered away, the total material simply does not add up to a full-sized planet. Second, models of the early solar system show that in this region between Mars and Jupiter, large worlds would have struggled to form at all. Jupiter's immense gravity disrupts the orbits of bodies in this zone, stirring them up so vigorously that they cannot easily merge into something larger. Instead of gently coalescing, big clumps would have been pulled into unstable paths, colliding and breaking apart into smaller pieces. According to these models, no object in the main belt ever grew beyond about 1,000 kilometers in diameter. The gravitational music played by Jupiter was simply too loud, too insistent, tearing potential protoplanets back into fragments. Evidence of these ancient collisions is still written in the belt today. Many asteroids belong to families, groups that share similar orbits and compositions. These families are like clans of stones, all born from the breakup of a once larger body. They drift in loose swarms, their paths still echoing the moment they were shattered. The boundaries of the main asteroid belt are not sharp lines, but blurred and soft, like the edges of a distant cloud. Most of its members orbit the Sun at distances between about 2.06 and 3.27 astronomical units. Within this range, however, there are distinct gaps regions where asteroids are surprisingly scarce. These are known as Kirkwood gaps, zones where Jupiter's gravitational pull establishes orbital resonances with the asteroids. Any object whose orbit places it in such a resonance will feel repeated nudges from the giant planet, gradually destabilizing its path and often ejecting it into a different orbit entirely. Because of this, the counts of rocks within those resonant bands are far lower than in the regions just beyond. Kirkwood gaps are not found only at the outer edges of the belt. They cut through its interior as well. 2 of the clearest gaps lie at about 2.5 and 2.82 astronomical units from the Sunday. Because of these patterns, astronomers often divide the belt into 2 broad zones, an inner belt and an outer belt, separated roughly by the gap near 2.5 astronomical units. At that distance, objects are in a strong orbital resonance with Jupiter, and many have long since been shaken loose. In the outer part of the main belt resides the largest object in this region, Ceres, the same world that once appeared only as a mysterious point of light in early telescopes. Over time, its classification has changed as our understanding grew. It was first considered a planet, then downgraded to an asteroid, and finally, in 2006, reclassified as a dwarf planet. What separates Ceres from most of its neighbors is its shape. Unlike the irregular chunks of rock that dominate the belt, Ceres is nearly spherical. Its gravity has pulled it into a rounded form, giving it the calm, complete silhouette of a small world. Ceres has a diameter of about 940 kilometers and a mass of roughly 9.4 times 10 to the power of 20 kilograms, about 1/3 of the total mass of the entire asteroid belt. Even so, it is about 6,000 times less massive than Earth, a tiny world compared to our own, but a giant among the rubble that surrounds it. Its orbit carries it between about 2.5 and 2.9 astronomical units from the Sunday. At its farthest, it drifts near 2.9 astronomical units. At its closest, around 2.5 astronomical units. Its surface can warm to about 239 Kelvin, roughly 33 degrees Celsius below zero. On average, though, it remains much cooler, with typical surface temperatures around 167 Kelvin, about 106 degrees Celsius, below zero. This is a realm where warmth never truly arrives, only degrees of cold. Beneath its airless, cratered surface, Ceres is believed to have a layered interior. At the center lies a rocky core. Around this core is thought to be a cryomantle, an icy layer, perhaps around 100 kilometers thick. Water ice may account for up to half of Ceres' total volume, and perhaps between 20 and 30% of its mass. A hidden reservoir of frozen water, locked inside a small, quiet world adrift between Mars and Jupiter. Far beyond the quiet orbit of Ceres, the main belt does not lose its complexity. It only grows more intricate, more full of small worlds that turn slowly through the sun's gentle pull. As we drift deeper into this region, the space between one rocky traveler and the next stretches wider than most people imagine. There are millions of objects scattered here, yet the emptiness between them is vast distances so large that even a lonely spacecraft could slip through unnoticed, hearing nothing but the hush of its own metal body gliding through sunlight. And within this stillness, the inner part of the belt holds a remarkable presence, Vesta. Among all known asteroids, Vesta is one of the largest and certainly the most massive aside from Ceres. Though smaller than its rounder neighbor, it stands out like a bright ember among coals. Its average diameter is about 525 kilometers, large enough to feel like a world with history, rather than a simple piece of stone. Its mass, around 2.6 times 10 to the power of 20 kilograms, is almost 4 times smaller than Ceres, but still immense compared to most of the rubble scattered around it. Vesta's orbit is slightly elongated. At its farthest, it drifts at about 2.57 astronomical units from the Sun, and at its closest, roughly 2.15 astronomical units. To complete one long, gentle loop around the Sun, it takes about 3.6 Earth years. During that time, as it moves from perihelion to aphelion and back again, the Sun's light changes its pale surface, causing tiny shifts in temperature that ripple through its crust. What draws our attention most is Vesta's unusual brightness. It is the only asteroid visible to the naked eye from Earth, not because it is enormous, but because its light surface reflects roughly 42% of the sunlight that touches it, far more than most dark, carbon-rich bodies surrounding it. When Vesta and Earth pass at their closest, about 177 million kilometers apart, or 1.18 astronomical units, the asteroid appears in the night sky like a faint star, quietly asserting its presence among constellations far older than itself. Its brightness is not its only distinction. Vesta is believed to be a fully differentiated body, that is, a miniature planet in all but size. Inside it lies a metallic core made largely of nickel and iron, wrapped in a rocky mantle. Long ago, when the solar system was still warm from its own creation, Vesta's interior was once hot enough for volcanic activity. Over time, the heat faded. Now its surface oscillates between -190 degrees Celsius and -20 degrees Celsius frigid, yet not entirely lifeless in geological terms. On Vesta's western hemisphere, dark plains stretch across the surface like bruises from ancient events. These regions may be basaltic lava fields, frozen remnants of volcanic flows that once poured and solidified under alien skies. Others believe the dark patches formed from violent impacts, collisions powerful enough to splash darker materials onto the surface. But the most striking feature of all is the colossal crater known as Rhea Silvia. It spans nearly 500 kilometers in diameter, almost matching Vesta's entire width. Its depth reaches 25,000 meters, an abyss carved by an impact so fierce that it scooped out a chunk of Vesta's southern hemisphere. At its center rises an enormous peak, reaching higher than 22 kilometers, making it one of the tallest mountains in the solar system. The collision that created Rhea Silvia must have been catastrophic, sending waves through Vesta's interior and launching countless fragments into space. Many of those fragments now travel the solar system as members of the Vesta family. More than 15,000 known objects with similar composition and orbit. These shards, broken from Vesta long ago, now drift as independent asteroids, making up around 5% of all main belt bodies known today. They are the children of a single, ancient calamity, still journeying through the inner belt like silent reminders of the moment their world was struck. Vesta's fate, its shattering, reshaping, and scattering echoes through many other asteroid families. In numerous cases, two large objects collided catastrophically, cracking into pieces. Some fragments eventually drifted apart forever. Others remained near one another. And over time, gravity gently pulled them back into loose clusters. But these new forms were no longer solid spheres. Instead, they became fragile piles of debris, collections of rocks held together only by the faint glue of mutual gravity. Astronomers, with a touch of poetic candor, sometimes call such objects rubble piles. One of the largest of these rubble piles is Silvia. Its twisted dimensions, 384 by 262 by 232 kilometers, give it an uneven, lopsided shape. Its mass, about 1.5 times 10 to the power of 19 kilograms, results in an average density only about 20% higher than that of water. This low density hints at vast caverns within, voids that may account for as much as 25 to 60% of its volume. Imagine a world not carved from solid stone, but assembled from drifting fragments that never fully fused an object that breathes emptiness within. Silvia takes about 6.5 years to orbit the Sunday. At its farthest, it swings out to roughly 3.7 astronomical units. At its closest, it dips to about 3.2 astronomical units. In this long journey, it carries companions, two small moons. Romulus is about 18 kilometers across, and Remus only 7 kilometers. They circle Silvia slowly, two faint specks shadowing a body built from rubble. Their compositions remain unknown, but it is likely they too are not solid worlds, but rather clusters of fragments held by gravity's gentle insistence. And some suspect there may be even smaller, unseen satellites, still hidden in Silvia's orbit, too tiny or too dim for us to detect. A little farther outward, another remarkable world waits. Pallas. Discovered in 1802, not long after Ceres, Pallas is the second most massive asteroid in the belt. With an average diameter near 512 kilometers and a mass around 2 times 10 to the power of 20 kilograms, about 25% less than Vesta, it balances delicately between sturdiness and fragility. What makes Pallas difficult to study is its orbit. It is dramatically tilted, leaning nearly 35 degrees compared to the plane of most planets. This steep inclination pushes Pallas above and below the usual pathways spacecraft travel when journeying through the inner solar system. Its orbit is also elongated. It takes about 4.6 years to circle the Sun, and during that time, its distance shifts from around 2.1 astronomical units at perihelion to roughly 3.4 astronomical units at aphelion, a change of more than 1.5 times. This motion, combined with its tilt, means that visiting Pallas up close is challenging. It weaves in and out of familiar paths like a cautious wanderer, keeping its secrets tucked behind geometric difficulty. Its surface is covered with more impact craters than Vesta's or even Ceres's, suggesting a long, tumultuous history. Studies of its chemical composition show that Pallas is mostly made of silicate rock, with small amounts of water and iron. Like Vesta, it may be one of the few surviving protoplanets worlds that began to form billions of years ago, but never grew large enough to become true planets. Pallas is a fossil of early solar history, offering clues about how rocky bodies formed, collided, broke apart, and evolved. Most other asteroids are far more modest. They cannot be seen with the naked eye, and many escape even amateur telescopes. One such elusive object is Inter Amnia, a dark, irregular world with dimensions of 362 by 300, 48 by 310 kilometers. Despite being one of the larger bodies in the main belt, Inter Amnia remains mysterious. It accounts for roughly 1.2% of the total mass of all main belt asteroids. Yet its surface is so dark that it absorbs about 93% of the light that falls upon it. That darkness makes it difficult to observe, even with advanced instruments. Inter Amnia belongs to the rare spectral class F, a subclass of carbonaceous objects. The reflection spectrum shows a remarkably uniform color, suggesting that this asteroid has not experienced large collisions in a very long time. Its density is only about twice that of water, hinting at a structure built from a rocky core wrapped in a thick icy shell, with fine, dark dust covering its frozen slopes. It takes Inter Amnia about 5 years and 4 months to complete a single journey around the Sunday. Along the way, its distance from our star shifts from roughly 2.5 to 3.5 astronomical units. In theory, Inter Amnia's orbit crosses the projected paths of Pallas and Ceres. Yet, despite this geometric overlap, the actual chance of collision is extremely low. The main belt is full of movement, but it is also full of emptiness. Even though millions of objects exist here, from dwarf planets to stones, the size of a cobblestone, the vast distances separating them mean that spacecraft flying through the belt face almost no danger. Hollywood shows ships dodging giant spinning rocks. Reality shows quiet space, scattered with distant silhouettes that hardly ever meet. Still, over long spans of time, millions upon millions of years, rare but dramatic collisions do occur. Roughly once every 10 million years, two large objects may finally meet in a destructive event that sends new fragments into orbit. These collisions replenish the belt's dust, create new families of asteroids, and gradually reshape the structure of this region. It is a slow, patient process, written across ages far longer than the lifetime of any species on Earth. Although humans will not visit the main belt in person anytime soon, several robotic missions have ventured here. The Dawn spacecraft spent years studying both Vesta and Ceres between 2011 and 2016, offering us stunning close-up views of two very different worlds, shaped by heat, impacts, and ice. More recently, NASA's Lucy probe lifted from Earth with the goal of exploring Jupiter's Trojan asteroids, but on its journey, it will pass through the main belt and photograph the object known as Donald Johanson. In 2025, a brief meeting on its longer pilgrimage, the Psyche mission, scheduled for launch in the early 2020s, aims for something different. The largest known metallic asteroid in the belt, a world that may once have been the exposed core of a growing protoplanet. The spacecraft is expected to reach its target by 2026 and remain in orbit for nearly 2 years, studying the asteroid's surface, interior makeup, and magnetic field. Through Psyche, we may glimpse the naked heart of a world that almost was an iron memory, orbiting quietly between Mars and Jupiter. In this way, even as we drift through darkness, the story of the main belt continues to expand. Each small world carries its own history, its own quiet voice, and as we move among them, listening softly, we begin to sense how many tales remain unwritten in the cold corridors of the solar system. How many worlds wait patiently for us to someday understand them a little more. Even as our quiet journey drifts through the cold stone and shadowed ice of the asteroid belt, there is still a deeper truth waiting at the edge of the mind, one that does not belong solely to planets or moons, but to the fragile threads that weave through everything. Worlds are shaped by gravity and ancient collisions, but destinies, too, can shift because of moments so small they almost vanish when looked at directly. In the same way, an asteroid's gentle nudge can break a family of rocks into new pieces. A single choice, or a shift in weather, or the faintest tremor of coincidence can tilt the course of human history. There is an old saying, often whispered when people try to describe this fragility, that the flap of a butterfly's wing in Brazil might one day stir the air enough to help create a hurricane in Indonesia. It is a poetic exaggeration, of course, yet at its heart lies something deeply true. The idea that tiny disturbances in a complex system can bloom into vast and unexpected consequences, long before it became a metaphor known to almost everyone. These ideas lived quietly in mathematics, and in the places where weather, chance, and destiny meet. To feel the weight of it, let us slip back into the world, not through the silence of space, but through the soft lantern glow of the past. It is the year 1893, and in Kyoto, Japan, warm summer air drifts through old wooden streets. Paper lanterns sway above stone walkways polished by centuries of footsteps. Among the travelers who wander through shrines and gardens is a young American lawyer named Henry Stimson, visiting with his new wife, Mabel White. They have come for their honeymoon, carried by curiosity and affection into a city whose grace lingers in the mind long after the journey ends. The couple walks beneath temple roofs that frame the sky like gentle hands. They listen to bells that hum across courtyards, watch the soft petals of late blossoms fall onto stone, feel the presence of traditions older than their own country. For them, Kyoto becomes a memory so vivid and tender that it nestles in their lives like a warm ember. They will recall it not only as a beautiful place, but as one of those rare cities that leave an imprint on the spirit. Neither could imagine then how that fondness, something so small, so intimate, might one day echo across the world in ways impossible to foresee. Half a century passes. The world changes, trembles, fractures. It is May 11th, 1945. In Los Alamos, New Mexico, inside a secure building surrounded by desert and urgency, a special committee of the U.S. Army gathers around maps and lists. Their task is grim: to determine priority targets for the use of a new kind of weapon, one unlike anything the world has known. On their carefully drawn list, Kyoto appears near the top. It is not only a major industrial center, they argue, but a city whose cultural importance makes it a symbolic blow. But then Henry Stimson, now the U.S. Secretary of War, sees the name Kyoto. He remembers its temples, its gardens, the serene beauty that once wrapped itself around him and his wife. He cannot bear the thought of that city vanishing in fire. And so, with a stroke of his pen, an act quiet and personal, born from a memory of lanterns and blossoms, he removes Kyoto from the list. Just like that, the path of destruction shifts. Hiroshima becomes the primary target instead. Weeks later, the tide of fate moves again. It is August 9th, 1945. The morning is heavy. The skies over much of Japan thick with humidity and low cloud. A B-29 bomber lifts into the air, carrying a weapon more powerful than the one used days before. Its mission is to destroy the industrial arsenal of the city of Kokura. The crew flies toward their target, but when they arrive, the town is shrouded in stubborn, dense fog. The smoke from previous raids clings to the air like a veil. The commander, Charles Sweeney, circles, searching, but the maze of cloud refuses to open. Fuel burns. Time presses. He makes a fateful decision to leave Kokura behind and head instead toward the secondary target, Nagasaki. And so, because of a blooming of fog, of weather drifting through a valley, of smoke that lingered just a little too long, the bomb falls, not on one city, but another. Millions of lives, across generations, shift as a result. All of it tied to a memory from a honeymoon, to a morning cloud, to choices made in rooms and cockpits where no one could see the full consequences of their actions. This story is not unique. History is a tapestry, woven with threads so fine we rarely notice them until we step back and see the entire pattern. We give this phenomenon a poetic name, the butterfly effect. But in truth, this flutter is only a single ribbon from a much broader and deeper fabric of science known as chaos theory, a field devoted to understanding why small changes can grow into vast differences in systems that are sensitive, interconnected, and unpredictable. To approach this idea gently, let us travel not far into the distant past, but just slightly into the latter half of the 20th century. It is 1961, and in a modest room filled with early computer equipment, mathematician and meteorologist Edward Norton Lorenz sits before a machine that hums and clatters like a mechanical heartbeat. He is trying to model atmospheric flows, to predict weather patterns with a precision that had never been possible before. With the new computing power of the era, he believes he might unravel the swirling complexities of clouds, winds, and storms. But the atmosphere is not so easily tamed. Lorenz divides his long calculations into stages, a strategy meant to save time. After each stage, he feeds the results back into the machine as the starting conditions for the next run. Some of the numbers are slightly rounded, just a few decimal places different. So tiny a change should hardly matter. It is the difference between writing down 0.506 and 0.51, barely a breath, barely a shift. Yet when he compares the output of the uninterrupted run with the output of the stage-by-stage run, the results diverge wildly. Two answers that should have been close enough to overlap, instead, veer apart like birds startled from the same branch, each spiraling off in its own unpredictable way. Lorentz is puzzled. The system of equations he uses turns out to be an incomplete representation of the atmosphere. It cannot fully capture the complexity of weather. Still, this unexpected divergence hints at something profound. His mistake, if it can even be called that, becomes a doorway into a new understanding. Patterns that should be stable instead behave as though touched by something delicate, like surfaces trembling at the slightest breath. In searching for clarity, Lorentz observes that when the solutions to his equations are plotted in three-dimensional space, they do not scatter randomly. They cluster around two looping forms, curving and folding in on themselves like petals or wings suspended in air. He calls these forms attractors points, or regions toward which the system tends to evolve, though never settling completely. When drawn, they resemble a butterfly with wings opening across invisible currents. What startled Lorentz most was how even the tiniest change to the initial conditions, a number altered in the third or sixth decimal place, could send the system swinging from one wing of the attractor to the other. The whole future state of the model changed. That shift echoed the same principle behind the stories of Kyoto and Nagasaki, that in systems woven from countless threads, the gentlest tug can reshape the entire tapestry. Lorentz was not the first to stumble upon this idea. Long before him, the German philosopher Johann Fichte and the French mathematician Henri Poincaré had spoken of similar effects. Poincaré, in particular, warned of how sensitive certain systems were to initial conditions, describing how a seemingly minor difference could grow into something enormous. But it was Lorentz who brought the idea into sharp focus, transforming what seemed at first to be an inconvenience, a rounding error, into a powerful and far-reaching theory that continues to ripple across science. Chaos theory does not claim that the world is random. Instead, it tells us that in certain systems, prediction becomes nearly impossible, because each small detail matters too much. Weather, the spread of diseases, ecosystems, markets, the sway of a spacecraft's path through regions of gravity, even the trajectories of asteroids gliding through the belt we just visited. All these things can behave in ways that resist perfect forecasting, not because they lack order, but because their order is exquisitely sensitive to beginnings we cannot fully measure. In a way, chaos theory fits perfectly into our quiet journey. It reminds us that the universe is not only vast and structured, but tender and precarious. Moons grow oceans beneath their crusts because of tiny shifts in orbit. Asteroids form families because of a stumble in a collision ages ago. And human histories can hinge on a cloud bank, a memory, a pen stroke. It is humbling and strangely comforting to know that even in a cosmos filled with giant planets, icy moons, and rocky worlds older than life itself, the smallest motions still matter. A butterfly's wing, a fraction of a degree, a single rounded number on a computer in 1961. All are threads in the tapestry threads that may stretch farther than we can ever fully see. Even as the idea of the butterfly's trembling wings fades gently into the quiet, something in the mind keeps drifting, as though the story itself still wishes to unfold. It goes without saying that in the decades that followed Lorentz's discovery, countless scientists, mathematicians, physicists, biologists, philosophers of systems, and patient observers of the world would each add their own careful thread to this tapestry we now call chaos theory. What began as a surprising quirk in the output of a humming computer slowly grew into a framework capable of describing storms, heartbeats, stock markets, the rise and fall of species, and even the shape of galaxies tearing themselves open in bursts of light. It is tender to think that something so vast could grow from something so small. Yet that is the nature of chaos. It stretches like a quiet river through all things, from turbulent airflow to the clustering of stars, from the way an empire rises to the way a continent slowly sinks beneath its own shifting crust. And if we wish to understand any of it with clarity, not to control it, but simply to see it more truthfully, we have to start with what chaos truly means in the language of science, a language far less frightening than it sounds when whispered slowly enough. One of the first things to understand is that even the wildest chaotic system still follows laws that are rigid, almost stern in their precision. There is nothing random about them. They are not the roll of a die or the pop of a quantum particle blinking out of existence. Their unpredictability does not come from disorder, but from rules so intricate that the smallest change in their beginnings makes the rest of the story branch out in ways no one can fully foresee. Scientists sometimes call this deterministic chaos, a phrase that sounds heavy, but only means that the future is set by the rules, not by chance, even if the outcome looks as unpredictable as weather caught between two stubborn winds. This is what sets chaotic systems apart from truly random ones. If we were dealing with something entirely stochastic, like the decay of unstable atomic nuclei, we could measure the average behavior over time, but never predict the exact moment when any single nucleus would break open and transform. For chaotic systems, things are different. If we could somehow repeat the beginning with perfect accuracy, the system would dance the same way each time. But if we nudge the beginning even slightly, shift it by a breath, a whisper, the faintest fraction of a degree, the result might stray into an outcome we did not expect. That is the heart of chaos. Sensitivity, not randomness. The formal mathematical definition sounds difficult at first glance, full of phrases like non-linear characteristics, global instability, oscillating equilibrium points, and fractal dimensions greater than 1.5. For most people, such wording presses too hard against the senses, like reading an unfamiliar script in the dim light of early morning. But stripped down to its essence, chaos rests on only a few soft truths that can be held easily in the hand. First, the system must be nonlinear. That means the world inside it does not respond in neat, additive ways. You cannot simply push twice as hard and expect twice the change. Instead, the response might steepen suddenly or flatten unexpectedly, curling into odd shapes like ripples that collide and amplify each other. It is the kind of behavior Lorenz stumbled upon. When the input shifts a little, the output may veer wildly, refusing to stay inside the neat boxes that simple arithmetic would prefer. Second, a chaotic system must be sensitive to its beginnings. This is the butterfly effect in its purest form. The notion that a tiny alteration at the start can transform the entire unfolding of events later on. It is not magic. It is simply the way certain systems stretch and twist small differences until they become impossible to ignore. The path of a leaf falling in swirling wind, the branching of a river delta, the flickering of a flame when someone opens a door far across the room. In such systems, beginnings matter more than we ever imagine. And third, the parts of the system must interact with each other in ways that overlap and intertwine, like threads weaving themselves into a pattern no single thread could predict. These interactions are the reason classical physics sometimes fails to describe the whole, because it tends to isolate pieces instead of watching them lean into one another. But chaos refuses to be separated. Its beauty lies in the way everything touches everything else, producing a structure that is both unpredictable and deeply real. To understand how deep this runs, let us drift our thoughts far beyond human time, further than mountains or oceans, or even the oldest of stars. Imagine, softly, the universe as it was 13.8 billion years ago, so young that only the faintest quanta of time had stretched themselves across its surface. Matter did not yet exist in any familiar form, nor energy as we know it. The four fundamental forces that now shape everything from atoms to galaxies were still intertwined, braided into a single strange unity. The laws we cling to today had not yet settled into their final shapes, and yet, even in that first trembling instant, the roots of chaos were already present. A tiny shift, anywhere so small it could never be measured, had the power to change everything. A slight imbalance, perhaps caused by nothing more than fluctuations of that primordial field, might have been enough to determine whether matter would cluster or dissolve, whether galaxies would form, whether planets would ever condense from swirling clouds. Our entire reality may have emerged because of these microscopic, delicate tremors that unfolded long before time had a name. Move forward, gently, 1,000,000 years. Space has cooled. The first atoms have settled into hydrogen, drifting in immense clouds that stretch across the dark like pale ghosts. There are no stars yet, no planets, no light except the afterglow still humming from the birth of everything. Gravity begins to tug at the hydrogen, gathering it into uneven clumps. Those clumps, each one jittering with internal motion, start collapsing into the first stars. They lie scattered in no particular order, like seeds blown across a silent field. And because each protostar is massive enough to pull at its neighbors, any slight change in its mass or its position nudges the entire region in a different direction. Chaos guides the collapse. Chaos shapes which stars ignite quickly and which linger in their infancy. And, over billions of years, those stars burn, swell, die, and explode. Their violent ends scatter heavy elements, the iron in blood, the calcium in bones, the carbon in every leaf across the vast dark. New stars rise from these remnants, surrounded by spinning disks of dust and ice. These disks swirl in complicated eddies, crossing paths, clumping, destabilizing, and settling again. Looking at them from afar, one could almost see the same patterns Lorenz once found. Loops, spirals, clusters, fragments orbiting invisible attractors in ways that echo the fluttering shapes of his butterfly-like diagrams. From one such swirling disk, about 4.5 billion years ago, our solar system emerged. Planets thickened from dust, moons condensed or were captured, rings formed and dissolved. Asteroids clattered quietly through cold expanses. Every rotation, every collision, every gentle nudge of gravity carried the fingerprints of chaos, of systems sensitive to beginnings, where tiny differences shaped the motion of worlds. And even now, so much remains unknown. The outer realms of our solar system are full of mysteries, their landscapes barely glimpsed, their histories still folded in darkness. Spacecraft have brought back a wealth of data from the giant planets, their moons, and the regions between. Yet much of that knowledge sits like puzzle pieces, waiting to be understood. Each answer sparks new questions. Each discovery widens the horizon instead of closing it. Despite the distance, despite the challenges, the slow and patient work of understanding never truly stops. Scientists continue to gather clues, sift patterns, refine models, and stare into the quiet tumult of the universe with the same wonder that first stirred Lorenz when he watched his computer produce two different futures from nearly identical beginnings, and because the universe itself is shaped by chaos, tender, intricate, sensitive chaos, there will always be more waiting beyond the edge of what we know. The cosmos is vast, but it is also intimate. It unfolds in grand gestures and tiny tremors, in the roar of a star exploding, and the subtle rounding of a decimal on an old machine. And the more we listen, the more clearly we hear that these things are not separate at all. They are part of one great shimmering fabric in which every motion, every ripple, every breath leaves its mark. Somewhere within that fabric, we drift too, small but connected, carried quietly by the same laws that guide the stars. And when we linger in this thought a little longer, something gentle rises, an understanding that chaos is not a threat to order, nor a force standing against harmony. Instead, it is the quiet engine that allows the universe to breathe and change. Without chaos, nothing new would ever happen. Stars would never collapse into brilliance. Oceans would never rise beneath frozen crusts. No moon would shift its orbit enough to warm a hidden sea. Even our own world would have remained a cool, silent stone, if not for the restless push and pull of cosmic instability that shaped its early past. In a sense, chaos is the universe's way of staying alive. It is the tremble in the web that keeps everything connected. And when we look back at our own lives, we find the same pattern echoed there too. A conversation overheard by chance, a letter arriving a day early or late, a decision made in the smallest moment of hesitation, someone choosing a different route home, a memory treasured, a kindness offered without thinking. These things, so fragile they almost vanish when named, guide the arcs of our lives as surely as turbulence stirs the weather or gravity shapes a spiral galaxy. And perhaps that is why chaos feels strangely comforting when understood gently, not as disorder, but as a reminder that the world is made not only of what we can measure, but also of what surprises us. The unpredictable is not the enemy of meaning. It is often the birthplace of it. Even the stars themselves owe their patterns to fluctuations so delicate that no instrument could have captured them. And still, from those fluctuations came everything we know: warmth, light, chemistry, time, the thin breath of life on a blue planet, and the quiet questions we whisper into the night. So as we rest here, imagining the universe unfolding in its patient, intricate way, it becomes clear that our place within it is neither accidental nor predetermined, but something softer, something shaped by a million interactions we cannot see, yet feel the echoes of. A universe governed by chaos is also a universe filled with possibility. It means that even the smallest moment can ripple outward in ways that matter. That uncertainty is simply the space where futures form. That complexity is not something to fear, but something to marvel at, like the shifting colors of distant nebulas, or the delicate frost that forms on a spacecraft window. And maybe, in the quiet of this moment, that thought brings a kind of peace. The cosmos is immense, filled with laws more subtle than we can imagine, and yet we belong to it completely. We are shaped by the same forces that nudged the first stars into being and stirred the early universe into its unfolding. The same sensitivity to beginnings that governs strange attractors also hums quietly in every story we live. We are, each of us, a small but luminous part of the same vast pattern, one shaped by gravity, by chance, by memory, by motion, and by the gentle, astonishing truth that even the faintest flutter can change the course of everything.